Thank you for your introduction. So what I want to present today is, as we heard, the initiation of asymmetric crack patterns in open hole plates as depicted here, loaded by tensile and also by bending stresses, basically. So after a short motivation, I want to introduce the structural situation that we examined, the failure models that we used. I want to validate those failure models real quick and compare the models against each other, and then talk a little bit about the impact of the hole size and the prediction of the crack patterns, or what crack patterns we can actually expect in this structure. We've seen that the coupled criterion is a very useful tool in order to assess the strength, or in order to assess crack initiation at stress razors by quite some authors. Some stress razors I've shown here, like rounded notches or open hole plates or such things. For the case of open holes, however, we've only seen symmetric loading, that is uniaxial tension, so where we also expect symmetric cracks on both sides of the holes. That's why I want to talk today about what happens if we load such an open hole plate by bending and tension, and therefore expect asymmetric cracks. Additionally, I want to compare the various formulations we know for the coupled criterion, the point-wise formulation, also referred to as point method, and the averaged evaluation of the stress criterion, which we also refer to as the line method. So the structure we examined for this present work is this open hole plate depicted up here in the top right corner. It has the length L, the width W, center hole of the radius R, and is loaded by a bending moment M and a tensile force N. We expect up to 3 cracks of finite size, delta A 1, 2, and 3, numbered top to bottom. For the analysis, I want to introduce a couple of non-dimensional parameters. One is this relative hole diameter, which just relates the diameter of our hole to the plate's width. Then we have the bending load contribution, lambda, which is essentially the amount of strain energy stored in an Euler-Bernoulli beam without a notch, if we load it by bending, related to the strain energy in such a beam loaded by tensile and bending loading. The denominator of this lambda will serve as our load parameter, we call it P, and then we have related crack length, which basically relate our dimensional finite cracks to the distance between the hole and the plate's edge, basically. The 2 models we used to examine the failure of this structure is a finite fracture mechanics approach and a cohesive zone model. For the finite fracture mechanics approach, we can obtain the stress and energy quantities we need for the coupled criterion using linear elastic finite element analysis. For the 10 parameters we have in our model, which are the loading, the geometry, the material properties, and also the cracks, we can reduce that to 4 parameters, 4 non-dimensional parameters, the related hole size, and also the 3 non-dimensional cracks, which we only have to consider in our parametric study in the finite element analysis. Basically, for all the other parameters, we can find analytical relations, or some of them, like the Poisson's ratio, I just neglected in this study. So if we basically want to examine any hole size of any size plate, we need to do a parametric study with about 80,000 finite element analysis, which run, due to their linear nature, very quickly on a standard SWC environment, which you used here in about 48 hours. If you compare that to the cohesive zone model, which requires nonlinear analysis and regularization, obviously that will require a little more resources. For the cohesive zone model, we investigated 2 different traction separation laws. One is this fairly well-known bilinear traction separation law, and then we also used a trilinear traction separation law, which we chose to resemble a Dugdale type traction separation law. And as I said, the cohesive zone model takes a little bit more resources, so if we just want to identify one single parameter point, in particular with this Dugdale type traction separation law, consumes about 72 hours on a desktop PC. As I said, we can obtain the relations for the stress and energy quantities using a couple of scaling laws. For example, if we use this finite element model depicted here, and we use a uniform scaling, that is, we scale the width equivalently to the length, then we can use two individual load cases, one with only normal force loading, one with only bending loading, and superimpose those using this law, which also includes our load parameter and the plate's width, where the subscripted not parameters reference our finite element solution to just obtain our stress quantities. The relation for the energy release looks pretty similar. We have the Young's modulus and this term which refers to the superposition of two load cases on asymmetric patterns. With all these stress and energy quantities at hand, we have to solve an optimization problem, which we heard before today, looking for the minimum load satisfying both our criteria, the stress criterion and the energy criterion, on any kinematically miscible crack pattern, and one of these crack patterns I've shown here just exemplarily. In order to validate our model, we can use experimental data available in the limit case of uniaxial tension here, for example, on these quasi-isotropic laminates studied by Camanio and Green and others. And in these experiments, we see a pretty distinct size effect, that is an increasing failure load with a reduction in the structure or feature size with respect to a pure strength of materials assessment. And this effect is rendered very well by the color criterion, which was actually seen before. In order to compare the failure models against each other, I want to have a look at the effect of bending. So if we plot the failure load and the corresponding crack length against the amount of bending which we impose on our structure, we see that at uniaxial tension, so lambda equals 0, we start with symmetric cracks at the hole, and as we increase the bending, the crack on the bending tension side of our hole starts to grow, whereas the crack on the bending compression side shortens. Until this point of transition in a critical bending and loading, we observe a sudden transition from the cracks at the hole into a single edge crack, which is associated to a kink in our failure load curve. The same trend as we've just seen for the line method evaluation of the couple criterion is observed for the point method, where the kink occurs a little earlier. And if we now superimpose the results of the cohesive zone law, we see that the cohesive model, the bilinear fracture separation law, agrees very well with our finite fracture mechanics results, in particular in this bending-dominated domain and in the tension-dominated domain, still pretty well with our finite fracture mechanics line method. The results of the trilinear cohesive law, if you recall it's a ductile type law, agree very well with our point method results in the tension-dominated domain, which actually recovers results we've seen in other publications, which found a very good agreement of the point method and the ductile type cohesive law for uniaxial tension. But we see that in the bending-dominated domain, we observe some deviation. If we look at the impact of the hole size, and we plot, for example, the critical bending moment we impose on the structure against the relative hole size, we observe this plateau of near constant failure load with respect to the hole size. In that solution, we can actually recover from the solution of the unnotched plate, which we can write in this form using stress intensity factors from handbooks in a semi-analytical manner, which actually also has been done by numerous authors before. But it's a nice result that there seems to be a critical hole size below which our the solution for a notched plate is valid for the solution for an unnotched plate is valid for the notched plate. And a pretty remarkable result of this work is that we can give this particular critical hole size as a function of the bending loading, obviously, but also the only second parameter that we need is the brittleness number. And this is a polynomial fit of fourth order. We have the coefficient matrix psi here. So we're a little astonished by this, actually. And just to give you a picture of what's possible with the coupled criterion in terms of asymmetric crack patterns, we can draw, for example, such a map where we have the relative hole size on one axis and bending contribution on the other axis, and observe that for small holes and relatively small bending loading, we would expect cracks at the hole. If we still have small holes but a larger, or substantially larger bending loading, we would expect a single edge crack according to the coupled criterion. And for sufficiently large holes, we would expect a single crack at the hole on the bending tension side. To conclude my talk, we've seen that the prediction of asymmetric crack patterns is very well possible using the coupled criterion. We could give a critical hole size below which the solution for an unnotched plate is valid for the notched plate, as well if we impose bending, which is a function of the bending loading contribution and the criticalness number only. We've seen a fairly efficient finite fracture mechanics approach. The modeling is kind of efficient. We've seen distinct size effects and also good agreements between finite fracture mechanics and experiments, and also with the cohesive